Greetings for everyone, and today I'm going to tell you the effect of the radiation with ions of different atomic masses of the properties of superlattices of cobalt, ferrum, cuprum, and to study the magnetic properties. Multilayer magnetic nanoheterostructure consisting of alternating layers of ferromagnetic and antiferromagnetic metals of nanometer thickness are in-demand materials for micro and nano electronics due to their characteristics effect of giant magnetoresistance, here and after referred to as GMR effect, which consists in a significant by tens of % decrease in electrical resistance when a constant magnetic field is applied. In addition, highly sensitive nanoelectronic devices in which superlattices with the GMR effect are widely used. Often, these need to be used under condition of exposure to ionizing radiation. There is practically no information about the behavior of magnetic superlattices under radiation loads, which is why these data are also of significant fundamental and practical interest. In this regard, the following tasks were set. First is to study the possible positive and negative effects of exposure to the magnetoresistive properties of superlattices when irradiated with inert gas ions of various grades in the fluence range from 10 to the 14 degree to the 10 to the 17 degree of centimeters in minus the second degree. The second goal is to study the radiation stability of nanometric films of cobalt, iron, copper, magnetic superlattices on substrates of monocrystalline sapphire glass and monocrystalline silicon. The third goal is to evaluate the contribution of purely thermal component and separate it from the radiation one during iron treatment. The object of our research was chosen by the more promising at the present moment superlattices cobalt, iron, copper, which you can see on the screen. The formula of the resulting superlattices is indicated on the slide, where the substrate is either, as I said before, a monocrystalline sapphire glass or monocrystalline silicon, in which the cobalt iron alloy is used together with the copper layers. Basically, cobalt iron copper superlattices are polycrystals with FeCC structure and a sharp axial texture in the direction 1, 1, 1, with the texture axis perpendicular to the substrate plane. For studies, the obtained plates, the plates you can see on the screen, of cobalt iron copper superlattices sample with a size of 3 by 8 millimeters were prepared, which are necessary for measuring the magnetoresistance. The slide just shown a sample fixed on a thin tungsten thread to exclude heat exchange with the surrounding objects. The multilayer magnetic nanoheterostructures of cobalt, iron, copper were obtained at the high vacuum sputtering plant manufactured by ULVAC, Japan. The installation shows the method of magnetron sputtering at direct current to spray thin films of magnetic and non-magnetic metals on substrate in various combinations. In order to compare the results of exposure of different types of ions, superlattices was irradiated with different types of ions. Argon and xenon ions with the atomic masses more argon and xenon, which atomic masses is greater more than 3 times than the mass of argon ions. Radiation with continuous beams of argon and xenon ions was carried out on a ELM-1 implant equipped with a pulsar 1M ion source based on a low pressure glow discharge with a hollow cold cathode. During irradiation of superlattices, the same beam parameters were used. The ion energy were the 10 kiloelectron volts, ion current density is 100 microampere per square centimeters. Fluences were chosen from 10 to the power of 14 centimeters to the minus of the second degree. This value used because the number of studies in literature have shown that the ion radiation with low fluences can lead to an increase the magnetoresistive effect. And we choose the fluence up to the 10 to the power of 17 to find the threshold values of fluences which the G-MER effect is preserved. The radiation was carried out by moving the samples under the ion beam, which made it possible to avoid the significant heating of the sample during irradiation. In addition, in order to completely prevent heating of the sample during a set of increasing radiation doses, irradiation was carried out using a specially designed rotary shutter, which you can see on the screen. This shutter ensures a uniform set of fluence by summing small exposures. The duration of single exposure is 1/10,000th of a second. The magnetoresistivity values of the superlattices was measured using an automated AVM1 installation, which is presented on the slide. The magnitude of the magnetoresistance is defined as the relative change in the electrical resistance of the material when the magnetic field is turned on. The calculation formula is shown on the slide. The resistance of the sample of the studied superlattices in a magnetic field up to 19.5 kilorastet is measured by a four-contact method with pressure contacts. The photo of this method you can see also on the screen, where pointed by arrow the contact needles and the sample. The vector of the magnetic field strength and the current during the measurements was directed perpendicular to each other in a plane of the film layers. The measurement was carried out at the room temperature. This slide shows the modes of irradiation with argon ions. As a result of the magnetoresistant measurements, it was found that the irradiation of superlattices with argon ions leads to a decrease in their magnetoresistance for all three types, regardless of the substrate material, which the fluence of ions in the order of 10 to the power of 14. I'm sorry to make these graphs very little, but I will show you with the laser point. With the fluence of ions in the order of 10 to the power of 14, these, and these, the magnetoresistance decreased slightly than the initial state. The superlattice retains its functional characteristics. When the fluence increases to the order of the 10 to the power of 15 and to the 10 of the power of 16, this, and this, it continues to decrease. The graphs show that the magnetic saturation field also decreases as the fluence increases, and the transition to magnetic saturation becomes more abrupt. At the fluence of the 10 to the power of 17, the G-MER effect, as shown on the slide, is completely disappears. A comparison of the magnetoresistance values after the ion fluence is set in various ways. By a continuous ion beam in a pulsed periodic mode using a shutter, when there is no heating of the samples, the curves F3 and F4 on the slide. The difference in values for a sample irradiated with and without heating on the sapphire silicon substrate is approximately about 2%. The exception is the sample on the glass substrate. Without heating, the magnetoresistance value is almost 10% higher, comparable to a sample that was irradiated with the continuous ion beam. This slide shows the modes of the radiation with the xenon ions. They are similar to argon ions. As a result of the obtained measurements, the radiation of cobalt, iron, copper superlattices with xenon ions also leads to a decrease in their magnetoresistance for all three types of substrate. The use of a rotary shutter during the set of the same fluences of 10 to the degree of 17 centimeters to the minus of the second degree, in the absence of heating of the sample, leads, as well as the case of the irradiation of argon ions, to a decrease in the values of magnetoresistance during irradiation. The difference in the values of the magnetoresistance depending on the method of irradiation is approximately 2% for samples of all types of substrate. The graph showed that the magnitude of the hysteresis of the magnetoresistance of cobalt, iron, copper superlattices practically does not change, despite a strong change in the shape of the magnetoresistance curve, and is approximately 38%. The magnitude of the magnetoresistance hysteresis depends on the perfection of the microcrystalline structure of the superlattice layers, and it is known that these types of superlattices are annealing at the high temperatures, and it is lead to increase the hysteresis during an improvement of the perfection of the texture in the 111 axis. At low annealing temperature, such changes do not occur. It can be assumed that the degree of change in the structure of multilayers and their interfaces caused by the action of argon and xenon ions with the energy of 10 kV at the fluences used in the insufficient for a radical change in a structural state of the studied superlattices. According to the literature and the data obtained by us, the decrease in the magnetoresistance of superlattices is mainly due to the process of mixing atoms of layers of different grades and change in the states of the interfaces. The slide shows the theoretical values of runs and losses obtained by the Monte Carlo methods. It is important to note that the zone of the intense mixing under ion radiation is approximately from 2 to 3 Rp, as shown on the slide, where Rp is the projected range over ions. The values of the average projective range of argon and xenon ions with energy of 10 kV are shown on the screen. The depth of mixing zone of atoms and the direction of the film surface to the substrate under xenon irradiation is slightly less than in the case of argon ions and is approximately from 8 to 14 nanometers. This is probably due to a slightly smaller effect of the action of the xenon ions on the magnetoresistance of the studied superlattices. The conducted studies allow us to conclude about the radiation resistance of cobalt, iron, copper superlattices. It is clearly seen from the graphs that the radiation resistance of these superlattices is higher than of the model iron chromium, with the iron chromium superlattices shown as the green line, green curve, on the slide, and where the modern superlattices, cobalt, ferrum, copper, is above. For detailed explanation of the behavior of the magnetoresistive properties of superlattices under radiation, additional structure studies are needed. And there is the conclusions. Thus, it is established that radiation with argon and xenon ions with an energy of 10 kV of superlattices starting with the fluence of 10 to the 16 degree centimeters in the minus of the second degree leads to a significant decrease in their magnetoresistance. When radiation with argon ions, the magnetoresistance drop is stronger, which is probably due to a larger average projected range and for accordingly to a greater depth of the mixing zone of atoms in the direction from the film surface to a substrate than for xenon ions. This is shown that the finding of cobalt, iron, copper superlattices is possible from several tens of hours to several days in the core of industrial power reactors, according to the obtained comparison of functional characteristics depending on the obtained fluid. The data obtained indicate that the main contribution to the observed change in the properties is made by ion radiation and not by thermal heating. And that's all. You're welcome to ask the questions.